This integration video follows on from the reverse chain rule, which we have studied in a different video, and also links to an earlier C4 topic of partial fractions. So let's look at integrating the function that we've got in front of us. The first thing I'm going to look at is partial fractions. So taking our original function of 6x minus 2, I want to break this up into my two partial fractions, a over x minus 2 plus b over x plus 3. So I know that 6x minus 2 must be equal to a lots of x plus 3 and b lots of x minus 2, simply by multiplying through by x minus 2, x plus 3. My next step is to use the roots, so I'm going to say if x is minus 3, what's that going to give me? Well, 6 times minus 3 is minus 18, minus 2 is minus 20. Minus 3 will cancel out my first bracket, and I'm going to end up with minus 3, minus 2, that's minus 5 from here, which tells me that b must be 4. And for my second root, if I just let x equal positive 2, this is then going to give me 12 take away 2, which is 10, which is equal to 5 lots of a, and again the b will cancel out, so I find out from this that a must be equal to 2. This now allows me to rewrite my integration as the integral of a over x minus 2, well that's 2 over x minus 2 plus b over x plus 3 plus 4 over x plus 3 dx. And now we're about done, because if we look at these functions we realise that these are going to be natural logarithm integrations. That is, that the first function here is going to integrate to give me 2 lots of log of x minus 2. The second function is going to give me 4 lots of the log of x plus 3, and of course my constant of integration. Now I can look to, if I want to, tidy this up and say that this will be the log of x minus 2 squared plus the log of x plus 3 to the power of 4 plus c, and again bringing these together using my addition law, this becomes x minus 2 squared, x plus 3 to the power of 4, plus my constant. So again, this is a question that's going to involve partial fractions, so I'm just going to rewrite this first of all as being equal to the integral of 4 over x minus 3, x plus 3 dx. And again I'm looking at partial fractions. This time I've got 4 over x minus 3 x plus 3 to be equal to a over x minus 3 and b over x plus 3. Again multiplying throughout by x minus 3 x plus 3 tells me that 4 is going to be equal to a lots of x plus 3 and b lots of x minus 3. Now substituting in, if x is minus 3, that's the root of my first one, so I end up with 4 being equal to minus 3 minus 3 makes minus 6, b, which tells me that b must be minus 1/3, and for my second root we'll let x equal positive 3. That's going to be cancelling out my second bracket to leave me with 4 is equal to 6 lots of a, which tells me that a must be 1/3. Now that I've got this, I can go back to my integral and again rewrite this. So I had 1/3 of x minus 3, so that's 1/3 over x minus 3 plus minus 1/3 of x plus 3 dx, Now looking to integrate these functions, again it's a natural logarithm integration, so this is 1/3 of log of x minus 3 and minus, from that coefficient on top, 1/3 of log of x plus 3, and again our constant of integration. Okay, again we can tidy this up. I can take out the thirds, and I could even go as far as saying that the subtraction here is going to be a division. And if I really wanted to, I could then go as far as to say that this is the third root of x minus 3 over x plus 3 plus c. But realistically, I would be happy with anything after this line here. Okay, in our final example, we are still looking at partial fractions, obviously. Slightly harder partial fraction this time, but only marginally. So I'm going to say that this is going to be equal to something to do with x, something to do with x squared, and my last bit with x plus 1. So let's head on down and sort out our partial fractions. So I know that 3x squared plus x plus 2 all over x squared x plus 1 will be a over x, b over x squared, and c over x plus 1. Being careful this time, because when I multiply through by x squared lots of x plus 1, obviously here I'm just going to end up with a lots of x plus 1, b lots of x plus 1, and c lots of x squared. Okay, now I'm actually going to start this time by just comparing coefficients, because looking carefully I can see that the only place I'm going to get my constant is going to be from my second bracket here, b multiplied by 1. So immediately from this I can work out that b must be 2. Once I know this, I can then go into other bits that I might want to find. So now let's use the fact that if I let x equal minus 1 as a root, then that's going to cancel out my first two bits and I'm just going to be left with c. So left hand side, evaluate that at minus 1, this gives me 3, this gives me minus 1, 3 take away 1 is 2, plus 2 is 4, and that tells me that c must be 4. And finally I'm just going to compare coefficients of x squared. So I know that I want 3 x squareds altogether. That's going to come from the ax times x, which is going to give me ax squared, and the only other place I'm going to get an x squared from is my plus cx squared. Well, I know from here that c is now 4, so 3x squared is the same as ax squared plus 4, which tells me that a must be minus 1. Now that I've got this information, I can go back to my integral and rewrite my integral now as minus 1 over x plus 2 over x squared plus 4 over x plus 1 dx. And looking through, the first term is going to integrate to give me log of x. My second term is going to integrate to give me minus 2 over x. And my third term is going to integrate to give me 4 lots of log of x plus 1. And don't forget our constant of integration. Again, I can tidy things up at this point. I'm just going to combine my logarithms. So this is going to be minus 2 over x. I'm going to write this as plus log of x plus 1 to the power of 4 minus log of x plus our constant, which is minus 2 over x plus 1 to the power of 4 divided by x, the subtraction here becoming a division obviously with our logarithms, plus our constant c. Thanks very much for watching. The next video I'm going to do is on trigonometric integrations.